In this video, I'm talking about the way that Hagen describes the use of units and being able to apply the dimensions from units to derive common engineering equations from physics. Now, I wanted to warn you that, remember we talked a little bit about Bloom's taxonomy, and there was this pyramid, and the things we see on the pyramid are remembering facts, and then next level up is understanding. Well, certainly this step requires some understanding of facts, but then I think really we're getting to the apply stage of the pyramid as we go up the levels of Bloom's taxonomy. And it occurs to me that that might be frustrating to you. If you haven't seen some of these equations, it's hard to make these leaps in levels. And so I just want to say to you, don't worry about that right now. We're still working on coming up the levels. I misspelled remember. Okay. Coming up the levels, and just kind of relax into it if you don't right away be able to jump all the way up to the apply stage. Okay, so here we go. The first problem I'm going to talk about is similar to problem 210, and I'm going to give you a quiz problem over problem 210 in the book. All right, so the idea here is we have a question: how much energy is used by a 60-watt light bulb for 120 seconds of use? Okay, and report your answer in joules. All right, so energy. Energy is measured in joules. Okay, you can deduce that from the question. And then you look into the tables that show up in chapter 2, and you'll see watts. And the dimensions for watts, W equals watt. Okay, the dimension for a watt is joules per second. Okay, so then the idea here is we know that energy is measured in joules, so let's sort of substitute for the joules. We'll put an E, and then we know time is measured in seconds, so substituting for time, we're going to put T. All right, and then this is a 60-watt light bulb, and if you looked in these tables, watts are used to measure power. Okay, so that's the equation that is derived. That's what he was talking about. You can take a look at the units, and it will, if nothing else, remind you of valid engineering and physics equations. All right, so you might not be at that level yet where you can just look at the units and deduce the equation. Okay, but certainly this is one to put into your arsenal of equations. Power is energy per unit time. Okay, so if we're looking at average power, it's the average energy per time interval. Okay, so we can then solve this problem, all right, since we know the equation. Okay, we are wanting the energy, so energy is going to be power times time. We have a 60-watt light bulb, okay, and then we need to multiply that by time in seconds, right? It needs to be seconds to be dimensionally correct, and so we were given this to be 120 seconds. Okay, so that would be in joules, all right? So 60 times 120 is 7,200 joules, okay? And if you use the prefixes like you saw from the reading, this would be 7.2 kilojoules. How did I get that? Well, you know, the K represents 1,000. Okay, so if I do 7200 and I multiply by 1,000, so K is 1,000, multiply by 1,000. To not change anything, I would need to divide by 1,000. So 1,000 over 1,000 is 1. Okay, then this 7,200 divided by 1,000 gives you the 7.2. All right, so you get to where you can mentally do that really quickly in your head. All right, so here is the answer to the first question from this video. All right, the next question, I think this is really interesting because I have access to the solutions manual, and the author really missed something there on problem 210. Okay, and so I just want you, I don't expect you to notice this. This is 2.10. Okay, but I did want to point out the problem that can happen when you just look at the units to try to derive the equations. You might miss something. Okay, all right, so in this particular problem, this is similar to problem 210 in your book. Okay, in this particular problem, we have an object that falls with a constant acceleration of 9.8 meters per second squared. Okay, so we know from physics that that's the gravitational constant of Earth in the SI system. Okay, and so what we're wanting to know is what is the average velocity for the first 10 seconds. Okay, and we'll get back to this assumption here in a second. All right, so if we take a look at this, 9.8 meters per second squared, that's the acceleration. Okay, so acceleration is in meters per second squared. We then ask ourselves, what is velocity? And I think, if you think back at it, velocity, miles per hour, meters per second. So you have a length divided by a time. Okay, and so velocity would be in meters per second. All right, so we can see that if I wanted velocity, I could take acceleration, but I'd need one of the seconds down in the denominator to be canceled. Okay, so if I multiply by time, that would do the trick. All right, so that's what he's talking about here. You look at the dimensions of the problem, the units, and you can deduce the equations. Okay, so here's the problem though. If you were looking for this and you were looking at the average, the average velocity, all right, the real equation for this is V of t is a t plus an initial velocity. And so for this formula to work, you really need to know the initial velocity, and then you could find the average over that particular time. So he neglected that step, and I wanted to just throw that out there just to tell you, hey, don't worry about it if you can't derive these equations from the units. It's not your time for doing that. Okay, so why do I discuss it? Well, it's mentioned in the book, and it is something that's good to think about so that you can develop your skills and move up in this pyramid to where you get to the point where you can apply things much quicker. You already know the formulas. The units just help you remind yourself of those formulas. Okay? All right, so finishing this example off, if we started at rest, the initial velocity is going to be 0. Okay, so this formula would still apply. And we could look at the average velocity over that interval. Okay, so we have V is equal to A meters per second, 9.8 meters per second squared, times T, and T is 10 seconds. Okay, so it looks like we get 9.8 times 10, which is 98, and then seconds cancel in the numerator, and I'm left with meters per second, which makes sense for velocity. Okay, so I'd like you to take these ideas and work the quiz problem and develop your skills as you move up this Bloom's taxonomy.